At a big enough scale, every software product produces lots of data. Whether you're building an advertising technology company, a social network, or a system for IoT devices, you have thousands of events coming in at a fast pace, and you want to aggregate them, you want to study them, you want to act upon those events. For the last decade, engineers have been building systems to store and process these vast quantities of data. The first common technique was to store all of your data in HDFS, the Hadoop Distributed File System, and run nightly Hadoop MapReduce jobs across that data. HDFS is cheap because you're storing data on disk. It's effective because Hadoop had this revolutionary effect on business analysis, and it's easy to understand what was happening. Every night, you take all the data from the previous day, you analyze it with Hadoop, and you send an email report to all the analysts. But of course, the problem was that this was a batch system, and you did not have the ability to react to events as they were coming in. You were just running nightly Hadoop jobs, and your application or your business would get updated the next day. The second common technique was the Lambda architecture. The Lambda architecture used a stream processing system like Apache Storm to process all incoming events as soon as they were created so that software products could react quickly to the changes occurring in a large-scale system. But events would sometimes be processed out of order, or they would get lost due to node failures, and to fix those errors, the nightly Hadoop MapReduce jobs would still run, and they would reconcile all the problems that might have occurred when the events were processed in the streaming system. The Lambda architecture worked pretty well. Systems were becoming real-time, and products like Twitter were starting to feel alive as they were able to rapidly process the massive volume of events on the fly. But managing a system with a Lambda architecture was painful. You had to manage both a Hadoop cluster and a Storm cluster. You had to make sure that your Hadoop processing did not interfere with your Storm processing. Today, a newer technique for ingesting and reacting to data has become more common. It's referred to as streaming analytics. Streaming analytics is a strategy for performing fast analysis of data coming into a system. And you only have to do it once instead of the Lambda architecture model of having to do things twice. In streaming analytics systems, events are sent to a scalable, durable pub subsystem, such as Apache Kafka. You can think of Kafka as this huge array of events that have occurred, such as users liking tweets or clicking on ads. And stream processing systems like Apache Flink or Apache Spark will read the data from Kafka as if they're reading an array that is being continually appended to. This array, the sequence of events that get written to Kafka, are called streams. This can be confusing because with a stream, you imagine this constantly moving, transient sequence of data. It's just streaming by and you have to capture it. And that's partially true, but data will stay in Kafka as long as you want to. You can set a retention policy for 2 weeks or 2 months or 2 years. And as long as that data is still retained in Kafka, your stream processing system can start reading from any place in that stream. The stream processing systems like Flink or Spark that read from Kafka, they're still grabbing batches of data. They're processing them in batches. They're reading from the event stream buffer in Kafka, which you can think of as an array. And this is something that confused me for a very long time, and I'm still wrapping my head around what exactly streaming means versus batch processing. If you're still confused, don't worry, we explain it more in this episode. Tugdual Grall is today's guest. He's an engineer with MapR, and in today's episode, we explore use cases and architectural patterns for streaming analytics. Full disclosure, MapR is a sponsor of Software Engineering Daily. In past shows, we've covered data engineering in detail, and I'm looking forward to seeing more data engineering topics and presentations. I'm attending the Strata Data Conference in San Jose next month, and if you're going to be there, please send me an email. I'd love to see you there. I love that Strata has been kind enough to give me a ticket. O'Reilly has given me tickets over the years since before I had a big audience, so they've always been very supportive of Software Engineering Daily, so I, in turn, am very supportive of O'Reilly Media. which is just a fantastic company. And if you want to know more about other data engineering topics, you can check out our app where we have all 650 episodes of Software Engineering Daily in a searchable format. We've got episodes about streaming architecture from companies like Uber. We talked to Matej Zaharia about the basics of Apache Spark. We've explored the history of Hadoop. You can find all these episodes by downloading the app for iOS or Android, the Software Engineering Daily app. And we've got recommendations and categories, related links and discussions around the episodes. It's all free, and it's also open source. So if you're interested in getting involved in our open source community, we have lots of people working on the project, and we do our best to be friendly and inviting to new people who are coming in and looking for their first open source project. You can find it at github.com/softwareengineeringdaily, and we very much appreciate anybody who checks out the community or joins our Slack. It'd be great to see you there. So thanks for listening, and I hope you enjoy this episode. Apps today are built on a wide range of backends, from traditional databases like Postgres to MongoDB and Elasticsearch, to file systems like S3. When it comes to analytics, the diversity and scale of these formats makes delivering data science and BI workloads very challenging. Building data pipelines seems like a never-ending job, as each new analytical tool requires designing from scratch. There's a new open source project called Dremio that is designed to simplify analytics on all these sources. It's also designed to handle some of the hard work, like scaling performance of analytical jobs. Dremio is the team behind Apache Arrow, a new standard for in-memory columnar data analytics. Arrow has been adopted across dozens of projects, like Pandas, to improve the performance of analytical workloads on CPUs and GPUs. It's free and open source. It's designed for everyone from your laptop to clusters of over 1,000 nodes. Check out Dremio today at dremio.com/sedaily. Dremio solved hard engineering problems to build their platform, and you can hear about how it works under the hood by checking out our interviews with Dremio CTO Jacques Nadeau, as well as the CEO Tomer Shiran. And at dremio.com/sedaily, you can find all the necessary resources to get started with Dremio for free. I'm really excited about Dremio. The shows we did about it were really technical and really interesting. If you like those episodes or you like Dremio itself, be sure to tweet at DremioHQ and let them know you heard about it from Software Engineering Daily. Thanks again to Dremio, and check it out at dremio.com/sedaily to learn more. Tug Grall is an engineer at MapR. Tug, welcome to Software Engineering Daily.
Thank you.
So I want to talk today about how to build streaming applications. And I want to start from the top about what a streaming application is and why these are starting to become more and more popular in all kinds of industries. So you've got all these different industries that create large volumes of streaming data. So you've got factories, sensors that are strewn throughout agricultural field. You've got oil refineries and all these big industrial systems that gather all these types of data. Then, of course, you've got ad tech. You've got all kinds of real-world systems that are generating tons and tons of data. But we have not had the tools to process those data streams in what some people might call real time. We'll get into what real time may or may not actually mean. But we haven't really had the great tools to do that sort of processing until recently. Maybe you could give a little bit of history on what were the tools that were being used in the past, prior to the days when we had things like Kafka and Flink. What were people doing to process these vast quantities of data?
Yes, so you raise a very interesting point about streaming and streaming the data, because companies have data for forever, and they have been moving the data around in a batch mode before. So the first part is, before even talking about streaming, is people were moving data, processing the data at scale or not, and you had a very good set of tools with Hadoop and the big ecosystem to do that on a very large amount. But more people were asking that I want to be able to get the data and process the data as they are created, as they are edited by users, by systems. You are talking about factories and sensors. The first thing that we have seen at scale, when I say at scale, it's on a distributed system that have to deal with millions of events. It was part also of the Hadoop ecosystem with Storm. Storm has been very successful to get the data in real time. But he had some challenges regarding the messaging part, moving the data around. So this is where new systems came into the picture, because all systems in messaging layer like GMS and MQ series, so all the message queuing platform, were great to work in a streaming kind of part where you were sending messages, but they had a lot of issues to scale and to really provide a flexible architecture for new applications.
Well, I think one of the big architectural shifts that happened was people started to converge on patterns around Kafka. So before people started to do that, everybody knew, okay, we've got all this data that's being generated by people clicking on ads or users doing various types of activity in systems where we just want to log their data, or factories or oil refineries or whatever. You've got all this data. And the ingress process, there was not convergence around that ingress process. So maybe, your data comes in and, you're buffering it to a file, and then you save the file to HDFS, the Hadoop distributed file system. And then later on, you run some batch Hadoop job on it. But that's kind of a messy process. You're just reinventing the wheel every single time. And it seems like recently people are starting to really figure out, okay, how can we use Kafka to be the buffer between the generation of data and the recording of data into our data lake?
Yeah, what you said about HDFS is correct. People were kind of tweaking the system to transform something that has been built for batch to try to do near real time. With MapR file system, we had a different approach because you can save on just flush data as they go. So you were close to what you can do with Kafka in terms of accessing the data. But as you mentioned, it's not only moving the data, it's also providing some interesting architecture choice in the way you want to build your application. First of all, you want to do that with many different people that are many different systems will push the data into it. So you were talking about ad industry with all the clicks and the views. So it will be dozens or hundreds of application servers working in parallel, generating all the data. You push that into a Kafka product, a Kafka architecture. So you work in parallel with failover, with distributed system to ingest. And then in a totally decoupled way, and this is a very important part, that you disconnect completely the source of the data from the potential targets. Who will consume the data has to be totally independent, because you want to keep flexibility to add new services, to new add business processing or data processing. So you have this nice architecture that can ingest a lot of messages. It is saved into the platform, distributed or reliable, and then you have consumer coming into the game where they have some interesting characteristics, like, for example, the scale is important. You can read in parallel from many processes, but also you can have multiple type of application reading the same messages, reading the same event. And this is where Kafka has an interesting part also, by providing an event log where you can replay if you want. You can either just say, I want to just subscribe and receive event for everything that is new when I start, or I want to redo and reread and consume all the message from the beginning. So this was not really possible before, not in an event manner. You had to read a large amount of file with no context, where in this case, you just have a very simple way of doing that.
You touched on something there, the segregation of reads and writes being pretty important. Is this the term CQRS, Command Query Responsibility Segregation? Is that the pattern you're referring to?
Yeah, it's one of the pattern. Is myself, I don't necessarily go in all these large architectures, because the reason why I don't, and it's really a choice, because you will always have people. It's like when we talk about RESTful architectures, you will have different way of achieving that, and people will never agree what we should do, what we should not do. But you are correct, is you will have some part of the system that is responsible of pushing and writing the data, and another part of the system will transform, query, and having something based purely on streams is you do that on the flow. The data are coming in, you just process, you just transform them the way you want with different tools. Because one of the key parts is when you are asking about what is a big change or what with previous architectures, is the fact that also the whole industries, all the tools now will be compatible and using the Kafka infrastructure. And even Mapr, we have built a tool called MapReduce that use the Kafka API to be able to leverage this ecosystem in the way you published and in the way you consume the data.
I'd like to dive in a little deeper into what a stream is and how people can think about streaming, because this is a confusing abstraction for some people. Because, we think about, if you're just an application developer, then you think about request response. Like you're building a service-oriented architecture, a microservices architecture. You build a backend that has some put requests, a get request. Those are one-by-one requests. But the data engineering conversation is often about these streams. So you've got streams of data being created. So how do we reconcile the idea of the fact that request response, like if I make a request to some endpoint somewhere, that is inherently a batch request, right? It's just one off request and I get a response, and that's one atomic request. But we talk about data in terms of streams. So this, you have this mental image of the continuous stream of data going from one point to another. How do we reconcile those two ideas of data being passed from one place to another?
Yes, so usually when I talk about streaming and when I start a discussion about streaming architecture, streaming processing and all this, I start exactly the way you mentioned is application developer will be very familiar with the request response. So you put some data in or you query some data, you have some processing, you have a result. You have another way of dealing with the data that will be the pure batch. You have gigabyte of data into a database, you have gigabyte of data into the file system or into a set of files, and you have a job that run on a regular basis to do some stuff, to calculate aggregations or to do machine learning modeling and all this. But you have something in the middle that is in fact the most important, in my opinion, and the most exciting part is the streaming. And one way of looking at it is, as you say, it's a continuous generation of data, a continuous generation of event. Or in a simple way I like to start is, if you look at the technical log you have inside your application, so you have your web application is writing every time you have a click, every time you have somebody looking at something in your application, you have an entry in the log file. And if you do that the old way, the old fashion of using this data will be you take the log file, you read the data every hour, and this is a batch. But in the same time, if instead of reading the file, and instead of writing each click into a log file, you send it into a messaging layer, you send it into Kafka, each of the clicks become an event. And the big benefits of that is you can say that I want to do something immediately when I receive the event. So instead of waiting every hour or having a request response as we have explicitly to say, I want to do this now, or every hour I will have something running, is I have an event that is generated by an application. It's somebody that's has logging to my applications on the web. This generates an event. This event is now inside the system. If you didn't build anything, it's there and it will stay here and you can still process it in a batch mode. You don't lose anything by doing streaming. You can still look at a batch being reading a subset or a large amount of events. But the interesting part is, if you say now my application, I want to react immediately when an event comes into the system. So you don't change anything to your architecture. You say now every click is sent to Kafka. I will build a consumer, so I will build a consuming application. And this application, every time if it's subscribed to this specific topic, this specific set of event, every time the stuff is generated, immediately, few milliseconds after, I will receive the data. And what I do with it, it's a different thing. The streaming base, it's moving the data, being able to publish the data in real time and consume the data in real time. Then when I have the data, we will talk about what we do in stream processing. It's when you get the data, you have to react. It's a big difference compared with request response or batch, because batch, you control the amount of data you want to deal with, same with the request response. Where you work with the streaming, you have your applications receiving one event, two events, three events, or maybe thousands of events one by one, but in few seconds or few minutes. You have to code a little bit differently to do the stream processing, to say, I want to detect if somebody, this specific IP address, is trying to log into my system multiple times in 1 second or too many times in 30 seconds. This is probably a fraud. And the nice part about that, and this is a big, big difference in the one way of looking between batch and traditional architecture to streaming, is instead of having a batch that will run every 2 minutes, you will have immediately one login, two login, three logins events, 5 or 6 login events trying to connect to the system in less than 30 seconds. You can write a program that will say, this is a fraud. I have to react on this.
Today's podcast is sponsored by Datadog, a cloud-scale monitoring platform for infrastructure and applications. In Datadog's new container orchestration report, Kubernetes holds a 41% share of Docker environments, a number that's rising fast. As more companies adopt containers and turn to Kubernetes to manage those containers, they need a comprehensive monitoring platform that's built for dynamic, modern infrastructure. Datadog integrates seamlessly with more than 200 technologies, including Kubernetes and Docker, so that you can monitor your entire container infrastructure in one place. And with Datadog's new live container view, you can see every container's health, resource consumption, and running processes in real time. See for yourself by starting a free trial and get a free Datadog t-shirt at softwareengineeringdaily.com/Datadog. That's softwareengineeringdaily.com/Datadog. Thank you, Datadog. So one way, that was a great explanation, great example as well, and so much to dive into there, but tell me if this is a correct way of thinking about it. So instead of thinking of it as streaming, which you could use that term, thinking of the stream as a data structure, it's an abstraction. People are making requests to some backend microservices, and those microservices are logging data to a stream, and it's a Kafka stream. And you've just got this long stream of logged events, right? And it's like those logged events are a byproduct of the request response. And then once you've got that long stream of events that is a byproduct, some of them are maybe going to be sitting in memory on Kafka. Some of them maybe have been written to disk on Kafka. But in any case, you basically have this abstraction of a stream, but it is a stream that you can read from at any point. You can take a subset of it from any point, as long as those data points are still on Kafka, and typically your Kafka retention policy is pretty long, or it's reasonably long, where you can say, I want to read all the events that happened from 2 weeks ago to today and aggregate data on them. Or you can say, I want to just aggregate like a sliding window of every 3 minutes. And the whole idea is that you have all this data accessible to you, and your performance characteristics are going to go up and down based off of how much of that stream you want to process at any given time, or how responsive you want to be to that, processing of inbound events that are being written to that stream. And it's just an easier abstraction to work with, to have this stream that is continuously being appended to, where you can start from any portion of it. It's just like a long array where you've got essentially constant time access to any place in that array, rather than the previous model where you've got this huge data lake, everything is on disk, and in order to do anything interesting with that data, you've got to spend a bunch of time pulling it in from HDFS and putting it into memory, and then starting to do a bunch of operations on it. With the Kafka abstraction, where you're writing everything to Kafka, then it's going to be a more performant, more flexible, And it's already segregated by topics, so you've already got essentially a schema across all of the actionable data in your organization.
Yeah, exactly. I think you mentioned the most important part that you mentioned really is when you have people emitting the event. So you have event 1, 2, 3, 4, 5 in this order. When you will read them, by default, you will read by 1, 2, 3, 4, 5, also doing any type of logic, or you can just take the new messages. And then what you said about the segregation, the organization of the data, you will have any number of topics, depending of the type of event, depending of the type of processing, or how you want to organize the data. It could be based on security and so on. On one of the pattern or architecture that you see, you will have event coming in from, for example, a factory generating many events on specific part. And this event is quickly processed, generating another set of different type of event. Let's take a very simple example. So you will have a lot of sensors in the factory generating events 1, 2, 3, 4, 5 for each with a timestamp and some metadata information. And one of them is about, for example, the temperature of one sensor. And if the sensor is becoming too hot, you will immediately generate a new event that will be an alert on a different topic to be able to provide information to another type of services. And you do that in a flow, in a real time, and with lot of flexibility in terms of development. You mentioned microservices before. Typically, this is where you will be able to quickly add new business logic, new processing, new services in a small amount of code running on its own. This is why it's a very nice way of doing microservices.
Yeah, you could call this enrichment or adding a new materialized view. So you gave an example of a temperature data. You could also have, you've got a bunch of, maybe I'm walking around and my Fitbit is periodically pinging the server and logging my location in some compressed GPS format. And then there's a data analyst sitting over at Fitbit, and they want to be able to analyze the data, and they don't want to deal with just GPS endpoints. GPS data points. They would rather deal with like a location. So you might have a small processing unit that takes those events and translates the GPS coordinates into something more rich, like Jeff is in Austin, Texas. He's walking at a pace of 3.2 miles per hour. And, a bunch of other data that you could gather from just a GPS coordinate, because, maybe it takes the GPS coordinate, takes the 3 previous GPS coordinates and calculates a velocity that I'm moving at. And that kind of data can be much easier to act upon. And what's interesting about Kafka is you could have 2 separate topics. You could have a topic for GPS events, and you could have a topic for enriched location data. And basically those are 2 materialized views of the same data, where you've got data coming in as GPS, and then it gets enriched and then written back onto Kafka, so that Kafka becomes this really flexible accessibility layer for different types of data. So in that example, what would be the best type of application system? Like, if I want to write this thing that is just a translation layer, that every time a GPS point is written onto that Kafka queue, I want to trigger an event that enriches it with location data and user velocity through space. Where would I write that? What kind of system would I write that in?
So you have different options. So the first will be the event layer that will be Apache Kafka or MapReduce, where we will be publish and consume information. So this will give you access to many things. When you have a very simple case, I will say this one is simple, you can maybe just use a simple Java applications or Scala applications or Python applications that will read the message, transform the location into a different format with a velocity, and emit using, again, the Kafka API to another topic. So this is something that you can still do, writing very small and simple application in Java and Python, doing basic transformation or basic enrichment. But it's one option in many, because sometimes you have some complex things to do, like time windowing, because what you want to do some complex calculation about the velocity, where you want to be sure to calculate the average speed on a sliding window every 5 seconds or something like that. So you start to look at that and you say, oh, it's becoming a little more complex to manage which type of tool I can use, because all the sample we are saying, they are working on very easy to do if you have, let's say, one event every second and you only have one or two users or two sensors or Fitbit in your applications. But suppose you are really Fitbit and you have millions of devices and you are distributed all over the planet and you have millions of messages coming inside the system. It's a different picture. So Kafka can handle that, no issue. Your small Java application, it will be a little more complex because you have to add more applications. This is where you will bring specific stream processing layer. And the two big things, or the three things we see on the market, is Spark with Spark streaming, Apache Flink, and also Kafka streams. All this will give you a set of libraries on API to simplify the development for doing stream processing, really consuming one or multiple events, take an action. And in our use case, the action is to transform that using your, let's say, Spark streaming. So you choose to develop, for example, in Scala. You do some time windowing manipulations, and you can emit another event into a new topic. And this topic will be the information that you send to other application.
Mm-hmm. That makes complete sense. So if we've got this example of writing, so let's take this example even further. So we've got all these Fitbits of lots of different users, and it's recording their GPS coordinates every 8 seconds or 5 seconds, and you want a streaming service that reads in those GPS coordinates, and maybe it reads in a sliding window of the most recent 10 GPS coordinates, and then calculates the user's current location, in terms of where they are, like the city they're in, maybe the country they're in, and their velocity, because you've got the last 10 events. So what would be if you've got tons and tons of users who are doing this at the same time, and you've got a choice? You can use Kafka streams, you can use Spark streaming, you can use Apache Flink. I think there's like a bunch of other ones. I know you mentioned just 3, but there's also Apache Apex and
exactly. You have many of them,
right? And then you've got Apache Beam. Maybe we could talk about that a little bit later, which is like that API for unifying them or something. How do you choose between those different streaming systems?
This is probably the hardest question you asked in the beginning of this podcast. The reason why I'm saying it's the hardest is because they all have very good characteristics and so on. So, for example, I will say my positioning today and the positioning we have at Mappa is because we have a complete support of Spark. When we say the complete support of Spark, it's not only the API. So we have experts internally in the company. A customer that is buying the product can connect and ask specific questions. And because Spark today is the biggest community, I will say, if you have to do some stream processing today, and you are okay with developing in Java, or even better in the case of Spark with Scala, you can work with Spark. And this is because I'm working on Mappa, and this is what I see the most. This will be my first choice based on supportability and community adoption. Then, if you look at this and you realize that, yes, but I need some more advanced capabilities in terms of time windowing and the type of window or the types of time that I can manage in event. And one of the big benefits of Flink is it has many ways of dealing with time and states of the event, the way you want to save it between different phases in the processing. So if you have very advanced work to do with the timestamp of the event, depending on what you call the timestamp, it's the event when it has been created by the sensor, it's when it's come into the system, or it's when it's processed by the system. So you have these options. And in this case, Flink could be a better use case. And we can continue the discussion with, for example, Apex. And I will say that also you have the community itself. For example, I am based in Europe, and in Europe, Flink has a bigger adoption than Apex. I don't know for the US, but for example, here, I will say that except if you are a big contributor and a big actor on the Apex community, in Europe, I will say look first at Spark, then Flink. And you have Kafka streams. Kafka streams will be for a lot simpler use cases, but the benefit, it's a lightweight library compared with the other. So in our story with Fitbits, I will go probably with Spark streaming first because of the size.
Because of the size of the community.
Yes, the size of the community, but also the size of the data, the number of topics on the partitions, on the way the architecture will be done, is just the size of the cluster that you will have to build will probably have some very lot of interest, because what we discussed today in this specific what we are discussing is really focusing on the streaming part, right? But you have other parts of your system. You may need to do some machine learning in parallel with the same data, on streaming data or not. You may need to do some analytics on the data in streaming or not. Because if we look at the pure streaming part, it simplifies the choice. You can say, oh, I just want to use Kafka/Mapper streams on some simple processing in Java on Kafka stream. But maybe I have other part of the applications where I have some data scientists that will build models and they are familiar with specific tools. So this is why I was saying it's hard questions, because you have to look at the full ecosystem, not as the tools, but ecosystem as the number of application and developer you have in the company you are working with, depending of the skills. Do they have what we see a lot is a part of some of data engineers/data scientists will prefer to work with Python a lot. So this is where, for example, the mix of Kafka and Spark will be interesting, because me as a core engineer, as a core data engineer, I will focus on moving the data, processing the data as fast as possible using Java and Scala. But my colleagues that will be the enrichment of the data with some specific model may use Python, and in this case, they will use Python on Spark. We are using the same cluster, we are using the same runtime on the same data set, no transformation of the data in different processing layers. So this is why I will say Spark on Spark streaming for this use case.
Okay, but it sounds like if we're talking about just that simple enrichment process,
yeah,
it's not that you think Spark streaming is necessarily the best tool for that case. It's more that you think that maybe you want to have multiple different uses for your streaming system, and like maybe Kafka streams or MapR streams would be better for that simple enrichment process. But if you're going to be also doing some large-scale machine learning across that materialized view that you're making with the user velocity, for example, you don't want to have to context switch between different streaming frameworks. You would rather just write it all in Spark streaming. Do I understand correctly?
Yes, and it will depend on the maturity of the team, the maturity of the enterprise regarding big data/streaming, because what we realize over time is my statement saying I will push Spark for this reason, it will say if it's the first big project people are doing with this type of architectures and data. Because going forward, people will be more familiar with distributed system as a storage or as a processing, and they may introduce new technology or different technology without being afraid of mixing, without being afraid of, okay, let's use Spark on Spark streaming for the machine learning part. Let's use Flink to do the alert system. So I will, in this case, have to runtime. But I like to always try, when I discuss with developers and architects or during conferences, to say, please keep it simple at the beginning and add complexity always when it's needed, because sometimes we just get a little bit too excited and we build very complex systems. They are already complex based on the volume of information, based on the distribution of the data. So in terms of frameworks, if we can start simple and add complexity only when it's needed, will be great.
So stream processing systems have this windowing process, like that's the time period over which aggregations are made. What's the difference between a window and batch processing?
So the batch processing will be, I want to take all this data or a subset of this data from this date to this date. Or let's talk about a database that will store all the events the same way. Instead of being stored in Kafka Mapper streams, they will be stored into a database. Take the data from the 1st of January to today and do some processing. And this is a batch part of it. When you will work with streaming and windowing, it will be a little bit different because the way you will do it, you will receive event and you have different options. You can say every 10 event, do this. So this one, it will be event by event. And keep in mind that when in the first example, I use a database, I will read all the records in one big batch. Where here, when I say wait for 10 events, or wait for 10 seconds, or wait for the first event and the second event in the time window of 10 or 20 seconds between the two events. This is something that could happen in different times. So when it's a time window, it will wait for the 10 seconds. But if I say 10 events, the 10 events could come in 1 second, or the 10 events could come in 2 minutes or 10 days. And the fact that you work with a time window, a count window of event, will give you a different way of processing the data. You will process the data exactly the amount of data as you want based on your business need instead of doing a big batch. So you will first not only be more reactive, you will react faster to the event, but you will also globally consume only the processing power and the time needed for the business you are trying to solve.
Amazon Redshift powers the analytics of your business, and Intermix.io powers the analytics of your Redshift. Your dashboards are loading slowly, your queries are getting stuck, your business intelligence tools are choking on data. The problem could be with how you are managing your Redshift cluster. Intermix.io gives you the tools that you need to analyze your Amazon Redshift performance and improve the tool chain of everyone downstream from your data warehouse. The team at Intermix has seen so many Redshift clusters, they are confident that they can solve whatever performance issues you are having. Go to intermix.io/sedaily to get a 30-day free trial of Intermix. Intermix.io gives you performance analytics for Amazon Redshift. Intermix collects all your Redshift logs and makes it easy to figure out what's wrong so that you can take action, all in a nice, intuitive dashboard. The alternative is doing that yourself, running a bunch of scripts to get your diagnostic data and then figuring out how to visualize and manage it. What a nightmare and a waste of time. Intermix is used by Postmates, Typeform, Udemy, and other data teams who need insights into their Redshift cluster. Go to intermix.io/sedaily to try out your free 30-day trial of Intermix and get your Redshift cluster under better analytics. Thanks to Intermix for being a new sponsor of Software Engineering Daily. These stream processing systems are often doing multiple stages of data transforms. So you might have a Spark streaming operation where you've got multiple stages of your pipeline, where you've got directed acyclic graph, essentially, of different operations that you're going to run over your data. It's going to go through the different stages in Spark streaming. And these transformations take time, and the stream processing system could fail during that period of time. You could have machine failures, and so that you have snapshotting. Like, these systems may snapshot data to disk. How do the different streaming systems that we've been talking about, like the Spark streaming versus Flink versus, Apex, how do the different streaming systems handle snapshot checkpointing? Is that one of the areas that they trade off against?
Yes, so you have different ways, because, for example, when we talk about the streaming part, your stream processing layer, Spark Streaming, Flink, or Apex, will subscribe to the Kafka topic, and you will receive event. And you can choose also, as you say, it starts the processing, read some events, start the processing, and maybe have a failure. First of all, you will have a first level kind of limit for your processing that will be when do I say to the Kafka that I have read or not the message? When do I commit the offset? When I say I have read this message and I have processed this message? Because you can say, until my full processing has been done, I don't want to say to Kafka that I have read this message. Like that, if I fail, I will reread the message. I will read all the message again and do the processing again. Then you have the snapshots or the state management into the different frameworks, where each of them here will have their own way of dealing with in which stage of my processing and how I can run and continue to run on different nodes. I personally have not looked in all the detail for the different frameworks here.
Okay, understood.
But a big part for me that when we talk about stream processing is how do you interact based on the Kafka model, where you read a message saying, when do I say to Kafka that I have read and processed this message? Because the principle is just we read it fast. We want to say, yes, I have committed this offset. I have read and processed or not this message.
Talk more about that. Why is that an issue that you focus on?
It's not an issue. It's just a choice of design. To make it very efficient to process and distribute the read of the log of all the event, you can choose to not commit every time you read the message, because it will be a little bit more expensive to say, I read this message, I am processing it, I read the second message, I'm processing it, I have to process the three message, the third and the two other together. You can choose either to send a commit for each message or just send when you are finished the job. If you do that at each messages, the risk is if your processing layer fail, and you don't have all the good snapshots and you don't know exactly what the state is, when the job will restart, you may not read the first message because you already said, I have read this message. If you choose to put the commit of the offset at the end of the processing layer, so if you have a failure when you read one message, two message, you start the processing, and you fail without sending the commit to the Kafka layer, what will happen if when it will restart, you will read again message 1, message 2, and continue the processing until message 3 arrive and do the job. And this is a type of thing that not only you do that when you do stream processing with Spark or Flink or Apex, this is also the way you work when you build your own consumer writing in Java, or when you want to work with tools like high-level toolings like Talent or StreamSet that give some nice tooling for the developers. They will use the same concept.
Understood. So you work at MapR, which has a data platform that combines a lot of these technologies that we've been talking about. And I think one of the goals is to make them a little bit more accessible and usable to organizations where maybe you don't have a giant fleet of distributed systems experts. So what are the kinds of customers that you encounter, and what kinds of systems do you want to build for them to make their lives easier?
So I will say any application from a traditional batch-oriented big data to a pure streaming like we talk about, or even interactive applications because we have a NoSQL database in the system. The main point of MapR, the way it has been built, in addition to provide a very rich file system giving read-write access to any file, you can store small file like big file. It's not like in a HDFS where you are limited, not limited technically, but you don't try to save small files. In MapR, you can use any type of files. But most importantly, if you look at it from the different stuff we have been talking, is you need a messaging or an event layer that is a Kafka cluster. You need to save the Kafka somewhere. So you may need a file system based on Kafka or a distributed file system to make it more reliable. You need a NoSQL engine sometimes to do some work on a distributed file system for very large file. What we have done with MapR, we put everything, all this, into a single platform. We have MapR file system, MapRDB, and MapR Streams. MapR Streams is using the Kafka API with a different way of storing the event. MapRDB is using the HBase API with a different way of storing the data. And same with MapRDB JSON, we have a JSON API. This simplifies a lot the architecture for a system administrator because they have a single cluster to put in place, a single security model. And then at the top of that, you use any open source project to build your application. Like we talk about Spark, you still have a lot of Hive and MapReduce job running. You can run a Flink job. You can run many things at the top of this application. So the type of enterprise is any type of companies. We have companies working in oil and gas industries. We have banks building their data lake in addition to transactions, listening for transactions, not for the pure financial stuff, but for regulations to be able to check compliance in real time. So you have many, many type of applications you can build with a simplified infrastructure.
And do they come to you with just like data strewn throughout their system in an unorganized fashion, and then they ask for help in getting it together and putting? So I think there's actually a lot of organizations out there who are, they're going through what might be termed a digital transformation. And, maybe the first step is probably even getting their version control system up and running, right? They're not even on the stage of digital transformation where they're building a data lake or doing a sophisticated analytics. They're just moving off of the FTP server, for example. So, for us that are deeply involved in the tech industry, it might seem like, oh, everybody's got an HDFS cluster with all their data, it's just like a big backlog waiting for a data scientist to come in. But there's actually a lot of organizations that do not even have that. So how do you see these large organizations getting started?
It really depends. You have people that come to Mapr just because they want a very powerful storage. Some people just want a better HDFS, a better file system for big data. So in this case, they have some maturity and they have a specific use case in view. But a part of our job, animating the community, participating to events, is to try to get some interest and traction, some discussing, to find a first use case that will get people exciting by building new services. It could be as simple as all these data sources, and I want to build a 360-degree view of something, 360-degree over my customer. And in this case, we have different approach. You can just help them with our professional services or the partner ecosystem to build step-by-step an application that will be this nice UI at the top of multiple data sources. And then you start to talk about streaming, and then you show that you can build processing and analytics in real time at the top of that. You have many different stages. The easiest way is where people have been working with big data for years now, and they start to think, oh, I want to build real-time applications. And I will come back to real-time in a minute. I think it's important to mention, where they will say, we need to move to streaming instead of batch, what we have talked about. We need a NoSQL database to build an application that will react very quickly. This is the easiest for us because they have started the journey, but we have different hooks depending on the customer.
Okay, so real time, what did you want to discuss with that?
Yeah, so when we talk about real time in big data in our area of expertise, is we are not building a rocket that we have to send to another planet. So we don't have to react in not yet, yes. So what we call real time in the project we are building and helping customer build is real time from a business point of view. It could be few milliseconds, few seconds, or few minutes. An example will be I am in a mall looking in different shops. What I want in real time as an application is I want when my mobile phone is recognized on the Wi-Fi network of the mall, I need to send some specific promotion, some specific content to my user in less than 1 minute. In this case, this will be real time and it's good enough. In another use case is I am using the platform to monitor all my applications. So I have Kafka, Mapper streams to listen all the logs we were talking about. And when I start to see somebody trying to do a fraud in terms of logging or an application that is becoming too slow, I have to react immediately. So in this case, it's few milliseconds to send an alert to another system. This is real time.
Right. It's a variable amount of time. It is real time depending on how low you need the latency to be.
Yes, and with all the framework we have today, we can adjust to that.
Yeah. Well, let's begin to wrap up by talking a little bit about the future and maybe some of your opinions. What are the unsolved problems in these streaming systems? What are the canonical problems that you're seeing where something just doesn't seem right? Like something is a little bit too hard and maybe we're going to see some kind of solution or startup or open source project in the near future?
So I think what we see quickly is all the security. How do you protect the data from the stream, and how do you make them available to specific set of users? So Mapr has started to work on this. This is, for me, the first part is a big thing that you have to solve. And for me, the biggest challenge that we see today is companies start to have very complex deployment in terms of they deployed in their own data centers, they deployed in multiple cloud providers, multiple geos all over the world, depending of the application. So we work, for example, with the ad management platforms that have multiple data centers in the US, multiple data centers in Europe and Asia, and they have to synchronize all the streaming in real time between all this. This is, for me, a big place where we have to continue to improve the platform to make that easy for the developers and the architects.
Last question. I don't know if you'll have a good answer to this, but we did a bunch of shows recently about these serverless tools, basically on-demand compute, where you don't have servers running continuously. You have sort of on-demand uptime that scales up or down based off of certain workloads. So, you know, I've had conversations with people about how this can be used with Kafka, but have you thought much about the opportunities for serverless, the on-demand computing model, for how that could impact streaming?
Yeah, so the thing is, what we are working on, it's not necessarily purely the serverless as what I see, and I think we should work on, and we started, is not only the pure serverless like the big cloud provider are providing, but more at least to use containerization, so Docker and Kubernetes to provide processing on the fly. So the pure serverless part will be adaptable of that, because what will happen is every time you will send the messages all over the place, you will have the application reacting to that. So yes, I think it's one of the most very exciting part of the new application we see building, but early stage for many enterprise. So the first investment we do and the enterprise are doing that we see, at least that I see, is really first about containerization of the applications and elasticity around processing of consuming the different events.
Okay, Tug. Well, it's been great talking to you. We covered a lot of stuff here, so thanks for coming on Software Engineering Daily.
Thank you.
If you are building a product for software engineers, or you are hiring software engineers, Software Engineering Daily is accepting sponsorships for 2018. Send me an email, jeff@softwareengineeringdaily.com, if you're interested. With 23,000 people listening Monday through Friday, and the content being fairly selective for a technical listener, Software Engineering Daily is a great way to reach top engineers. And I know that the listeners of Software Engineering Daily are great engineers because I talk to them all the time. I hear from CTOs, CEOs, directors of engineering who listen to the show regularly. I also hear about many newer, hungry software engineers who are looking to level up quickly and prove themselves. And to find out more about sponsoring the show, you can send me an email or tell your marketing director to send me an email, jeff@softwareengineeringdaily.com. And if you're a listener to the show, thank you so much for supporting it through your audienceship. That is quite enough, but if you're interested in taking your support of the show to the next level, then look at sponsoring the show through your company. So send me an email, jeff@softwareengineeringdaily.com. Thank you.
Wow.